You know that sinking feeling when you're just staring at a 504 gateway timeout on your screen? Or when you're watching an API totally choke under heavy load? Yeah, we've all been there. The truth is, in the world of cloud and DevOps, networking isn't just some optional side quest. It is the absolute backbone of everything we do. It's the invisible layer connecting your compute, your storage, your databases, and your security. So today, we're diving into a full-blown networking masterclass. Because understanding this backbone, that's your golden ticket to solving those frustrating timeouts, scaling your systems effortlessly, and really mastering your infrastructure. All right, here's our game plan for today. We're going to breeze through 5 main pillars, taking you from basic networking all the way up to AI-level performance. Let's kick things off right at the foundation with Pillar 1, Core Fundamentals, literally the building blocks of the internet. Think about it. Without an address, you just can't deliver a package, right? Now, we've basically been running out of the classic 32-bit IPv4 addresses since the 1990s, but honestly, they are still absolutely everywhere. IPv6 is the modern upgrade, giving us a practically unlimited 128-bit address space. But notice the super crucial difference in how they're built. IPv4 uses a time-to-live field, while IPv6 swaps that out for something called hop limits. When a packet passes through a router and that limit hits 0, it just drops. It is a brilliantly simple safeguard to prevent packets from just endlessly looping through the network forever. But just having millions of IP addresses isn't enough. We've got to organize them. Enter CIDR, or Classless Interdomain Routing. This is a super efficient notation system that lets us carve up massive networks into smaller, secure little neighborhoods, or subnets. So if you see a /24, that just means the first 24 bits are locked in for the network, leaving the rest for your actual devices. You're going to use this every single time you design a cloud environment. But hey, quick warning, overlapping your CIDR blocks across 2 different networks will completely break your cloud routing. Seriously, ask me how I know. Always validate your ranges. Okay, so an IP address successfully gets your data to the right machine. Think of it like finding the right apartment building in a huge city. But once you're in the lobby, how does the machine know which specific application should actually receive that traffic? How do you find the right door? Boom, the answer is ports. The port is that specific apartment door. If you're messing with container mapping, you absolutely have to know the heavy hitters. Port 22 for SSH, 80 and 443 for standard and secure web traffic, and 6443 for the Kubernetes API. And right alongside ports, we have protocols, basically the rules of the road for transmitting that data. TCP is your super reliable delivery driver who always asks for a signature, while UDP is way faster, but, just throws the package on the porch and speeds off with no guarantees. Oh, and don't forget BGP, that's the critical routing protocol calling the shots on the best paths across massive cloud networks. To really visualize how all this connects, we use networking models. You've probably seen the OSI model. It's that highly theoretical framework with 7 distinct layers, going from physical cables all the way up to the application layer in your browser. But in the real world, the internet actually runs on the TCP/IP model, which simplifies everything down to just 4 practical layers. Why does this matter to us? Because when things break in production, you're going to diagnose the issue layer by layer. If a packet isn't routing, you've got a network layer problem. But if an SSL handshake fails, now you know you're debugging up at the transport layer. Moving right along, let's step up to Pillar 2, Physical Network Infrastructure. How do we actually move this data across the wire? Let's meet our physical traffic directors. First up, hubs. These are basically the noisy neighbors of the 90s. Mostly obsolete now because they just blindly broadcast everything to everyone. Next, we have switches. These are your local directors, using MAC addresses to map out and route traffic within an immediate neighborhood. Finally, routers operate a level higher. They are the major highway interchanges, relying on IP addresses to connect entirely different networks together across the globe.
Now, what happens when you have, say, 50 devices in an office, but only one internet connection? Enter NAT, or Network Address Translation. It's a vital process running on your routers that translates all those private internal IPs into one single public-facing IP. It conserves precious address space and ensures your internal devices aren't just sitting out there exposed to the open web.
DNS. We all know the classic DevOps joke, right? It's always DNS. Because humans like easy domain names and machines only understand IP addresses, this crazy multi-step dance happens every single millisecond you browse the web. Your browser checks its local cache first. If it's a miss, a recursive resolver jumps in and asks the root server, then the top-level domain server, and finally the authoritative server to fetch that exact IP address. Pro tip, when your app breaks, always check this chain first. Okay, let's take all those physical concepts and virtualize them. Pillar 3, cloud networking concepts.
Welcome to the VPC, your virtual private cloud. Think of this as your very own isolated VIP section inside a massive public cloud. Inside, you carve out subnets. Your public subnets are internet-facing, which is perfect for your load balancers and web servers. They talk to the world through an internet gateway. Your private subnets, on the other hand, are highly secure with zero direct internet access, making them the perfect safe house for your databases. If those private resources desperately need a software update from the web, they have to securely route outbound-only traffic through a NAT gateway sitting over in the public subnet. But here's the thing. Even with incredible cloud routing, physics is still physics. Light only travels so fast. If your servers are in India and your users are in the US, that data takes time to travel. That is exactly why we use CDNs, or Content Delivery Networks. By caching your static assets on edge servers physically located right down the street from your users globally, CDNs bypass those physical speed limits and totally slash latency. Plus, when you pair them with web application firewalls, they actively block malicious traffic and swallow massive DDoS attacks before they ever even get close to your origin server.
All right, things are about to get really dynamic. Let's hit Pillar 4, Containers and Distributed Systems.
So when you run Docker containers, they obviously need a way to talk to each other. Docker actually gives us 3 main modes for this. Bridge mode is your default, setting up a private, isolated network right on the host machine. Host mode completely strips away that isolation, sharing the host's network directly if you need lower overhead. And overlay mode is what you use when you need multi-host communication across a whole cluster. Now keep in mind, container IP addresses are totally ephemeral, meaning they literally vanish the second a container restarts. So you absolutely have to rely on Docker service names to communicate, never hard-coded IPs.
Now, when you level up from single containers to full-blown Kubernetes, there are 2 golden rules you just have to memorize. Rule 1, every pod gets its own unique IP address. Rule 2, every pod can communicate with every other pod without ever needing network address translation. Now that sounds super clean and simple on paper, right? But implementing it under the hood is wildly complex. Thankfully, all that heavy lifting is handled automatically for us by CNI plugins like Calico or Cilium. Let's actually break down how that communication flows in Kubernetes layer by layer. At the most granular level, container-to-container communication just happens over localhost because they share the exact same network namespace. Stepping up a level, pod-to-pod traffic gets routed via those CNI plugins using specific pod IPs. But since we know those pod IPs are always changing, pod-to-service communication uses a sneaky little component called kubeproxy to load balance the traffic to a stable, reliable virtual IP. And finally, to let the outside world in, external-to-service traffic relies on ingress controllers to expose the clusters safely. But what happens when you have literally thousands of microservices scaling up and down constantly? Keeping track of all that traffic is an absolute nightmare. Enter the service mesh. A service mesh injects a little sidecar proxy, think something like Envoy, into every single pod. Suddenly, all traffic going in and out routes through this proxy. It is brilliant because it handles all your complex traffic management, automated retries, and even secures communication with mutual TLS. And it does all of this without you having to rewrite a single line of your actual application code. Which brings us to our final stop, Pillar 5, Security and Performance, the overarching shields of our infrastructure. For years, corporate security basically operated on a trust but verify model. If you were logged into the corporate VPN, you were trusted. But today, we really have to challenge that. Why shouldn't we trust our internal network? Well, it's a massive shift called zero trust architecture. Zero trust demands that we literally never trust, and we always verify every single request, whether it's coming from outside or inside the building. So if a hacker manages to compromise an employee's credentials, zero trust stops them from moving laterally through the network, because every new system they try to touch is going to challenge them independently. And at the end of the day, you simply cannot fix what you cannot see. This observability toolkit right here is your lifeline. Network monitoring keeps an eye on latency, throughput, and packet loss in real time. Network logging captures your VPC flow logs, which is absolutely critical for doing the detective work after an incident occurs. But remember that 504 gateway timeout we talked about at the very beginning of this explainer? When a request has to hop through 20 different microservices, distributed tracing is the absolute lifesaver that tracks its exact journey, letting you find the precise bottleneck that caused the crash. Let's pivot for a second and look at how networking dictates the absolute bleeding edge, AI infrastructure. A lot of engineers actually mix these two metrics up, but in AI, they are very distinct.
Bandwidth is basically the width of the pipe. It determines the overall throughput of all those subsequent AI tokens being generated. Latency, however, is the delay. In AI chatbots, latency totally dictates the time to first token. You know that snappy streaming response you get the second an AI model starts typing? That relies entirely on ultra-low latency and requires incredibly high-speed hardware interconnects under the hood.
We are way past the days of manually plugging physical cables into hardware routers. Today, software-defined networking, or SDN, completely decouples the physical hardware from the software layer. The actual intelligence dictating where your traffic goes is fully software-driven now, making your entire network 100% programmable and infinitely scalable. So, as we wrap up this explainer, I want to leave you with a thought. Armed with the real power of programmable networks, zero-trust security, and scalable service meshes, how are you going to architect your next system? Take these concepts, apply them to your own environments, and go build something amazing. See you next time.